Hi there, good afternoon, and welcome back to the next lecture in this theoretical series on structural equation modeling. Today, I'm going to try and take you through a step-by-step guide on how to go from the idea of the model that you want to test right through to getting to your first structural model. Hopefully, you'll find it fun. So first, just a reflection on what we've already done. We had a brief reflection on what regressions are. We had a nice overview of the basic concepts in structural equation modeling. And now we're going to go into the most fun part, the part where you're here, is how do we estimate these specific models? So as I mentioned in the previous lecture, to get to your structural model, it takes about 5 steps, right, in order to help us to do any structural equation model. The first one is model formation. And this is basically, remember, SEM is a confirmatory factor analytic technique, right? And it's therefore based on theoretical assumptions that we have. So there needs to be a theoretical argument underpinning the reason for the model that we want to test, right? Because it's basically hypothesis testing. Model identification means even now that we know what this model looks like that we want to test and the different versions of the model, there needs to be enough free indicators or pieces of information in the model that we've measured that help us to actually estimate the factors that are unobserved. In other words, there needs to be enough things that we've observed, so enough free information to help us to estimate things that are not there. So, for example, if we want to measure the relationship between happiness and performance, we don't measure physically the relationship between happiness and performance. We estimate it. It's not there, right? So because of that, we have to draw a degree of freedom from somewhere to help us to estimate that specific function. So and there are different types of models, identification models. Once we figured out what this is, we can actually go and estimate our model. We can actually go test it. Now, the purpose of model estimation is basically try and minimize the difference between the amount of observed items and implied factors that we want to kind of assess. And we do this kind of through this iterative process, right? To try and see which model basically fits our data the best, how we want to reduce the amount of chaos, basically. So we want to say as much as possible with as less as possible words. We want to declare as much variance with the least amount of chaos, basically. Once we've systematically assessed all of the different models, we can then really go and compare them. So we evaluate the models and we see if we have to modify them. That's the 4th step. Here we use certain fit statistics and certain criteria to 1, figure out does the data fit the model, and 2, which model fits the data the best? How do we compare different models with one another? We really are, like I said, concerned with what we call absolute fit, which is does the models fit the data, and comparative fit. Can we compare it with others? And then finally, once all of these things are in place, it will help us to generate our structural model, the thing we're actually interested in. All right. So let's get to the first one. So model formation basically refers to correctly specifying the structural model or the measurement model based on the theoretical assumptions that underpin it. The model can be formulated either based on broad theory that we have or on other empirical research that has been done in the past. So these are the 2 things that we can kind of use as indicators for justifying the model that we basically want to test. Now, there are basically 2 parts, and I'll explain in a minute, but we have measurement models, which is basically the relation between the different factors, and we've got structural models, which gives it directionality. So those are the 2 fundamental models that we can test. Now, as I mentioned in the previous slide, models that we are going to test are representations of theoretical assumptions that we have derived from the literature. So we have the theory tells us a certain thing, and we want to test whether or not this thing kind of works in reality. What I kind of always do is I always suggest that always physically draw a picture of the path model that you want to test, the different path models. So It's basically, if you say happiness, what does happiness look like? How many items does it have? How does it relate to other factors? But physically draw the path diagram on a piece of paper based on theory, because that will show you what you need to test. Okay? And I'll show you how it looks like in a moment. So based on these pictures, we have these two models. We have the measurement model and we have the structural model. The measurement model basically looks like this. It is certain questionnaires or certain item factors that's made up of certain items. So you've seen exploratory factor analysis, so we know that certain items load on certain factors, and that gives us an indication of that factor, right? So here we've got three factors made up of different items. They're correlated with one another because they're freely estimated. We don't give it directionality. Once we figured out what the best fitting measurement model is, so once we've looked at 20 different models and tested them and compared them, we then transpose or create a structural model based on the best fitting measurement model. Now, where the measurement model is correlational and it shows covariances between it, so we don't give it directionality, the structural model is our dependent model, right? So it shows dependence or directionality. So we want to see how does demands lead to engagement, lead to task performance. Okay? As soon as we transfer it into a structural model, the exogenous of these engagement and task performance, they get residual variances on them as well, where in measurement models, that's not necessarily the case. So I keep telling you that we need to test competing measurement models with one another, but we have to figure out what's the best model for our data. Now, there are three strategies that you can employ. We usually employ a combination of two of them, but I'll start with the one that you should avoid at all costs. It's called the model development strategy. Here you have a whole bunch of items that you've measured, and you systematically build the model based on what the data says, based on what you assume. But it's basically a developmental approach, and it means that after you've got the set model, you have to go test it again against another sample and another sample and another independent sample in order to kind of like confirm it. So I'd stay away from that approach. The approach that we usually employ is a combination of confirmatory factor analysis and competing measurement models. Okay? So you know a confirmatory factor analysis is we have an assumption about the theoretical structure of a concept, but we also know that concept has different permutations. So if we have happiness, and I'll show you in a minute, there's different components, we know that certain items load on it, and we've got different versions of that questionnaire or that construct, and we test them against each other in the competing measurement modeling strategy. So confirmatory, we're confirming the factor structure, the factorial validity. Competing measurement modeling strategy, we take that and we compare different versions of it with each other. Basically, what this means is we want to see who's the strongest, right? We've got two superheroes, and we've got the lizard villain. We throw them into a arena, and we want to see which one of the three comes out the strongest, right? Of course, we're all rooting for my main man, Deadpool, but let's see what happens. So in practice, this is what it then looks like. We have one instrument, which is called the Authentic Happiness Index, for example. And we know from theory there are three versions of how this thing can manifest. They can say, also it's made up of the instrument we use has basically 8 items, right? So the theory tells us it can manifest in 3 ways. It can be 3 paths to happiness in isolation, so meaning, engagement, and pleasure on its own. It could be that meaning, pleasure, and engagement in combination with one another leads to happiness, or happiness can just be a function of all of the items in totality, right? So this is a CFA model, a confirmatory factor analytic model, and 3 different versions of them. So we're going to estimate them and test them against one another to see who is the strongest, and we'll do that at the end. So basically, this approach seeks to determine if the number of factors and the loadings of the measured indicator variables, so the items, conform to what we expected them to be like based on theory. Indicator variables are therefore selected on the basis of a priori theoretical assumptions and our factor analysis is used to see how these specific items load on those factors between the different models that we have. Okay, now that we know how to get to how to draw or what we want to assess, we have to go to the next part, which is model identification. Now, this is, for example, going to look for the questionnaire, for example, to measure happiness. It's important to understand that model identification is a property of the model itself and not of the data, right? The data does not play a role here. So you have to plan this stuff before. So your questionnaire needs to have enough items. There needs to be enough people. There's a whole bunch of factors that you have to consider, but it's a function of the model, not of the data. Okay, so this step specifically determines whether there is a unique solution in our data for all of the free parameters in our model. Model estimation by itself cannot be implemented if a model is not identified. It cannot run. And model estimation can not converge. So if there's not enough free parameters for the things we want to estimate, your model is not going to run. It's not going to converge. Okay? So I'll show you how this works. Like I said, we want to ensure that there's enough free information available on the data to help us to specify the things that's not there. So if you think about the relationship between, again, happiness and performance, we're estimating the relationship. The relationship is not measured, but we have to get information or free parameters from somewhere to help us to estimate that. Now, I'll show you just two equations, right? Well, one equation. So we are basically going to see the amount of stuff that we basically want to estimate. We can check by the amount of items, observed indicators, plus 1 divided by a half. That's kind of like the small equation that we use. And there are three types of identified models. It can only manifest in three ways, model identification. The first one is what we call just identified, a just identified model, right? Where P is, of course, the number of non-redundant parameters. And this is the function of the amount of observed indicators. So that's item 9, item 8, and item 7, plus 1, because we want to create a standardized value, times a half. And that gives us 6. We then basically have 6 parameters that you can use to estimate something. Okay? But we have, what do we want to basically estimate? So we can use 6 things. We've got 6 degrees of freedom that we can use to estimate 6 things. But how many things do we actually have to estimate in this small little model? We have 3 error variances, so E1, E2, E3. We have 2 factor loadings, so for 8 and 9. Why? Because item 7 is, the factor loading is always constrained to 1. One item is always constrained. One factor loading is always constrained to 1 because it's utilized that to estimate the other 2. So we estimate 3 errors, 2 factor loadings, and 1 latent error variant, 1 latent factors variance. So that tells us if we've got 6 parameters that we can use, we have 6 things we need to estimate, so there's no degrees of freedom left, and that's perfect. Okay? Problem is if there's an issue with your items, then it becomes a major issue. Fundamentally, we've got enough free parameters in our model to help us to estimate what we need to estimate. The next type of model is what we call an over-identified model. Now, an over-identified model is actually what we want. So we want a little bit more parameters available versus the amount of parameters that we want to estimate. So same equation. So we basically have 4 observed indicators. There are 10 free parameters that we can basically utilize. And how many parameters do we have to estimate though? So we've got 10. We've got 4 error variances, 1, 2, 3, 4. 3 factor loadings, 8, 9, and 10. Why? Because 7 is constrained to 1. And we have to estimate 1 latent factors variance. So this thing that doesn't exist, we have to estimate. So there's 8 parameters, and we've got 10 factors. Grade 1 mathematics tells us if we have 10 apples, and Sana wants 8 apples, that leaves us with 2 apples left. And that's amazing. We can move on. So this is the type of model we always want. But unfortunately, we also have under-identified models. And this is where the problem comes in. Let me show you. Take the same equation, 2 observed indicators. That tells us we basically have 3 free parameters that we can use to estimate things. The problem is that we have to estimate 4 things because we have 2 error variances that we have to estimate, 1 and 3, with 1 factor loading for number 9 and 1 latent variance, 4. So, first grade mathematics tells us if we have 3 apples and Sana wants 4 apples, we're not going to satisfy her needs. So we are short 1. When you run this, oh man, you get the following error in A+. Non-convergence, number of iterations exceeded. And that's a major problem. But don't worry, we can fix it. But how do we fix it? Of course, prevention is better than cure, right? You can go look for an instrument that measures demands by 20 items, for example. So it's important to plan these things way before. But there are 3 things that we can do statistically to help us to at least get the model to run. The first thing is we kind of try and constrain the 2 paths, the 2 factor loadings, to be equal, right? Because if we constrain it to be equal, we at least gain 1 degree of freedom, okay? So if we have 2 error variances, we have 1 latent variance, and we have 0 factor loadings, we've got 3 parameters, but we still have to specify 4. But at least it starts to give us 1 extra degree of freedom. Another thing that we can do is we can constrain the latent factor to 1. So what happens is that the little 1 that's on this constraint is taken off, right? And it's basically moved to demands. So the variance then is kind of like moved to demands. So we can do that, or we can do a combination of, okay, yeah, still 3. Or we can do a combination of both, where we constrain these items to be equal and we constrain that error to be 1. And therefore we have then 4 parameters that we need to estimate. We have 4 parameters we need to estimate, 2 parameters that we need to estimate, and we have 3 factors. So we are pretty much in the right. Now, like I said, there are a couple of things you need to consider when that can influence convergence here. The first one is if you get standardized betas bigger than 1 on your loadings, there's an issue, and you have to investigate. Usually, it has something to do with the error variance or the distribution of a certain item. But if you get standardized betas bigger than 1, you've got a problem. If you have negative residual variances, that will also lead to non-convergence issues. What you can do there is you can constrain the residual variance to be 0 or positive. That will also help. If you have a very small sample, of course, you're not going to get convergence. And if the relationships between factors are extremely high, so you have multicollinearity, that will also result in non-convergence. So these are 4 things you have to consider, statistically at least, in the model identification process. Okay, now we have that in place. Now we get to the fun stuff. So model estimation, this step basically involves the estimation of all of the parameters in your model, and we generate what we call fitting functions, right? So we generate fit statistics. Now there are various estimation methods that you can use in SEM, and I'm not going to bore you with them. We're only going to talk about maximum likelihood. And again, the fundamental principle of the maximum likelihood estimation method is that data needs to be normally distributed. Okay? So we basically specify in our model, in our program, how each factor looks like, and we run it. Easy as that. Okay. Now we get to the final part. After we've estimated meaningful model parameters, you need to assess whether or not the model that you have actually fits the data, and then after that to see if which of the 4 or 5 or whatever models that you've tested is the best, right? If the model fits the data very well and the results are interpretable, then the modeling process can basically stop, right? So you systematically test stuff until you get to the best fitting theoretical model. If the model does not fit the data, right, we have to re-specify or modify the model in such a way that it can actually converge, that it does provide us with good fit statistics. And I've already made a video about that on one of the micro lectures. So in this instance, for example, we can make a decision on either to delete an item, modify an item, correlate items, whichever way you deem fit. But the problem is that every single thing that you do, every choice you make to improve fit, model fit, you have to be able to have a good rationale and an argument for that. All right. So once the model is then re-specified, we can kind of like go through the same process again. Now, there are two things that's important here. The first one is what you call fit statistics indices. So your statistical program will, of course, generate betas and blah, 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 but it also generates fit statistics. And there are a couple of things that you need to consider. And again, we don't just take, there's not just one item that tells us, oh, our model is great or not. We have to look at a combination of factors because we have to build an argument to support the decision that we make at the end. Like in a court case, you can't just say a guy's guilty because he was at the crime scene at the time of the murder. There needs to be a whole bunch of other factors. He has to have the gun in his hand. There needs to be DNA evidence. So there needs to be a bunch of factors that you use to be able to justify the decision to send him to prison or not. And the same case here, to justify the decision based on the model that you choose. Good? Couple of things important. Firstly, chi-square. Chi-square is this indicator of model misfit. In the perfect world, the models that we test, we want to have a chi-square of 0. Unfortunately, that will never happen, right? So the larger the chi-square, the more the indicator of misfit. We want a non-significant chi-square here, okay? Important. So it needs to be as close as possible to 0 and non-significant. The problem is if we compare different models with one another, we want a significant difference between the models that we're testing. Okay? Hope that's clear. With RMCA, root mean square error of approximation, we basically want a value that's generated that's like no bigger than 8, 0.08, right? And the confidence interval that it generates, it should not go through 0, right? Important. SRMR, the same thing. It needs to be smaller than 0.8, okay? And then we've got the two other factors that I usually look at first, CFI and TLI. You need to have it needs to be bigger than 0.9 for you to actually even consider the model to be a good model. And it's also the one I kind of like primarily use to quickly compare different measurement models with one another. Comparative fit, the same thing. AIC and BIC values, it's not an indicator of fit, but you can use it to compare fit between different models. So the lowest AIC and BIC values between the different models that you're testing, the lowest one is the one that gives you an indication of the best model. The same with chi-square. If we have 3 models, one model has a chi-square of 100, the other one of 200, and the third one of 300. The measurement model that has a chi-square of 100 is the best because it is lower than 300. The same with SRMR. The same with RMISA, the same with SRMR. The incremental fit stuff is the opposite. So the highest TLI and CFI is the best. So if we've got one model that has 0.9 and another one at 0.92 and the other one is 0.95, model 3 with 0.95 is the best. Okay, so this is the criteria that we use. However, even if you get a model that fits the data perfectly, right, it does not necessarily mean that that's the best model for your data. A lot of research has shown that excellent fitting models is a function of poor measurement quality. So you always have to look at model fit first, of course, but then also look at measurement quality. And what do we mean by measurement quality? I will show you that in a minute. So let's quickly just take this as an example. We ran a specific model, and this is the outcome data that was produced. So help me to say, does this model fit the data? Let's look at chi-square. Oh, shoot. So chi-square, it's non-significant. which is what we want. We can't directly interpret chi-square, so it doesn't mean anything. Here's a problem. RMCA is 1.02. These this criteria, the 90% confidence interval doesn't include 0. Oh, and it's also significant. Okay, issue. TLI and CFI is larger than 0.9, so that's good. SRMR is just slightly over the 0.8, I think. So looking at this, even though if you look fast, it looks like it fits the data, this is not a very good model. And this is why we have to also take consideration measurement quality. Now, there are a couple of things we have to look at. Firstly, we evaluate every model based on our fit statistics, right? So every theoretical model that we test empirically, we have to generate the fit statistics on it, so this thing, and then we can compare it with one another so that we can get the best one, right? So we can determine the best one. Once we have that in place, we have to look at the factor loadings, the standardized factor loadings, to make sure that all of the items actually load bigger than 0.4 on their respective factors, and they all need to be significant. Our residual variances, these need to be as close as possible to 0, and they need to be very small and significant, right? Also, every questionnaire that we have needs to be reliable. It needs to be, you have to estimate composite reliability to check if the level of internal consistency of the specific questionnaire. And there are various ways. You can use Omega, McDonald's Omega, or Rho, or whatever. You can even use Alpha, Cronbach Alphas if you want. That's not composite reliability, but it is a reliability. But that at least gives you some identification, right? And then after we've run all of these models and we've got good fit, we can go and try and improve the fit through correlating some error terms or something with the model. So let's look at this practically again. So these are the standardized results of that model. We want to make sure that all of the factor loadings, so all of the estimates, are bigger than 0.4. Yes, they are. We want to make sure that all load significantly. Yes, they do. Right? So they're all bigger than 0.4, and they're all significant. Good job. Residual variances, they need to be as close as possible to 0, and they need to be significant. So there's only a few of them that's close to 0, right? Most of them, there's a lot of residual variance. So there's a lot of noise in them. But interesting, so one of the factors that we're estimating here, so psychological well-being, is non-significant. And this is probably where our major issue occurs. That's why we got those weird fit statistics. It's probably because of how psychological well-being here is specified. So, quick homework. We want to test these two models, a one-factor model for happiness and a three-factor model for happiness, right? These are our fit statistics for the two models. Pause the video quickly and check which model do you think fits the data the best, looking at the criteria we used before. Okay, welcome back. So let's look. Here we see chi-square. It is significant though, unfortunately. But that's also a function of the small sample size, which is like 320, I think. But 580 is smaller than 870, so this model fits the data the best. RMCA 0.05, 0.07. Model 1 fits the data the best. CLI and TFI are bigger than 0.9, and they're bigger than the other model, right? 0.84. And SRMR is 0.06, and there it's also bigger. So model 1 is clearly the best fitting model. But how do we interpret this? So there's two things we have to do. We always have to describe our model. So this is kind of the first thing that we would write. We'd say in order to determine the best fitting model for the data, a competing measurement modeling strategy was employed, where two theoretical confirmatory factor analytic models were estimated and compared. Model 1 was happiness was estimated as a three-factor model made up of pleasure with 3 items, meaning 3 items, and engagement 2. And model 2 is made up, happiness is one factor model. So we always specify this in the beginning to tell the reader what it is that we assessed. And this is then how you of course, put this all in the table because you have to report all of the fit statistics. But this is what you write up. The results showed that model 1, all of that fit statistics, fitted the data significantly better than model 2. That's how you interpret it. Straightforward, right? I think so. So now that we know what the best fitting measurement model is, we can go and transfer that into our structural model. So we have our correlational model now, and we transform it into our structural model. So we changed directionality. What did you notice? All of these little lines disappeared, the covariant lines, and they became little arrows, straight arrows, because we give them now directionality and create dependence of some sort. So this is what we then specify in our actual model, right? So this is the model that's then basically generated, and there are certain things that we kind of have to look at. Of course, we have to determine the validity of the structural model. So we look at the overall fit. It should not, unless there is something really wrong, the fit statistics should pretty much stay the same between your measurement model and your structural model. We are focusing on our structural model specifically on determining the direction of the relationship, right, and the strength thereof. Okay. The emphasis here is specifically on the strength of the relationship and the variance that we are basically generating. So work role fit predicts 27% of the variance, and it's like 0.52 is the strength of that specific relationship. We have to focus on the standardized factor loadings here, not the unstandardized ones, because otherwise we can't compare. And we only report paths that are significant. So in this case, this is kind of what we have found. So how do we interpret this? The first thing is we speak about the overall fit. In our paper, we say the structural model was estimated based on the best fitting measurement model, and the structural model was shown to be acceptable, shown to have acceptable fit. Then we get to the most important thing. How do we interpret this? So work role fit predicted 20% of the variance in meaning, and similarly, meaning predicted 33% of the variance in task performance at that strength. Right. But the problem now is all that we have here is work role fit predicts meaning and meaning predicts task performance. But we don't know yet if what's happening in work role fit, so the amount of variance that's predicted in meaning by work role fit, does that actually affect task performance? And that is something for our next video, where we're looking at mediation and indirect effects. Ladies and gentlemen, thank you very much for your time, and I really hope that you found this meaningful and insightful. Talk soon.